So this image might seem a little strange to have here. This is Pandora's box. And so maybe a little imaginatively, I like to think of binary black hole mergers as everything escaping from Pandora's box, and what we're left with, rather than hope, is final mass and spin. So that's what I'm going to talk a little bit about. And I don't consider the in-spiral parameters evil, but I'm just saying. So I'm really going to focus on the merger. So I find it absolutely fascinating to think of the fact that we're sitting there seeing the nonlinear merger in the detector, and as we heard yesterday, that just is going to get better and better. So what information is available to us in this nonlinear regime, and what can we measure from that, is what questions I'm asking myself. So this image is, oops, I never use these because I'm not this good at it. This image is of two black holes merging. So we're used to seeing the gravitational radiation being emitted by these two black holes merging. Instead, this is a picture of what the horizons look like right when we transition from two individual black holes to a single merged black hole. And something to keep in mind is that in numerical relativity, which is producing this movie, when we look at horizons, we do so locally. So these are called apparent horizons. And an event horizon would actually form a little bit before this big blue peanut that you're seeing up here. And so these highly distorted horizons that we're getting right at the merger of the two black holes has got incredible information available to us if we can just disentangle it. So what I'm looking at is a situation where we went from the many parameters of in-spiral down to the few parameters of Ringdown, how we lose all that information. That information is encoded in the gravitational waves. And its numerical relativity is going to provide us that map of how we excite quasi-normal modes, what kind of harmonics get turned on because of different masses and spins of the black holes initially, and basically how do we lose all this information and how do we recapture it here on Earth. So those are some of my goals at the moment. So one thing to keep in mind as we look at this, and this is a cartoon, obviously, that I totally made up. And so the idea here is that multiple paths can lead to the same remnant black hole. So because we start out with so many parameters, we end up with so few, you can imagine that you have your final black hole and its spin magnitude and orientation could come from a variety of different initial setups. These are so cartoon that I didn't check that they all would actually give you the same final mass and spin, so don't go check it because it's probably not true. But I just wanted to get the idea in your head. So we have the situation where you might not be able to disentangle exactly which scenario produced that final black hole mass and spin. And what that looks like in the data, so if you do a bunch of numerical relativity simulations, and these are all of aligned to anti-aligned, so that means spins are down, and then as you change the magnitude, the spins are aligned of the two black holes. So each one of these is a plot showing you, each dot is a numerical relativity simulation where you're starting with a particular mass ratio of the two black holes. Yellow is horrible, and it's a mass ratio of 0.2. Green is mass ratio of 0.4, and blue is a mass ratio of 0.6. And so what you're seeing is, in each one of these little families here, the cluster, is the spin magnitudes are changing. So you go from anti-aligned to aligned spins, where the magnitudes are going 90% of maximal down to 0, Schwarzschild black hole. So this is the final spin and the final mass. And so what you can see is, for some of these, it's going to be pretty hard to disentangle what different scenarios might have led to that final black hole because there won't be enough difference in the final mass and spins to disentangle them. So it can be hard to distinguish these remnants. And of course, what you see is that the more different the two black holes are, the more information we might be able to disentangle even about their final state. So the caveat to this that we haven't really talked enough about, I think, recently. It was really popular when we got our first numerical relativity runs to actually work, because it was our first astrophysical statement ever. So the community was pretty excited about gravitational recoil there for a while. And what gravitational recoil is, we heard about it just now from the idea that you can kick a black hole out of these globular clusters or galaxies. Here I'm sort of agnostic about what the formation of the black holes are. They exist. I just study them theoretically as a solution to Einstein's equations. But what we know is that even though the final mass and spin of a certain configuration might be the same. So if we have a situation where we have two black holes where they're processing spins, What really will matter here is what the spin orientation is when it enters the merger regime. That's what determines how much kick there is. So it's a very nonlinear effect. So kick, although it is true that it's an asymmetric emission of radiation due to our emission of linear momentum, what's fascinating about kick is that the magnitude of that kick really is completely dependent on what the parameters are right when they enter the nonlinear regime. And that's where you get the big kicks. And so that means that even in a scenario where we have the same final mass and spin, you could disentangle what type of initial spin vectors you had if they're precessing, because they would lead to different recoil. So we actually could get a measure, in some sense, from gravitational recoil. And I like this plot over here by Rizzola, because he actually came out with a beautiful explanation of what's called anti-kick, which is the slate deceleration seen here in this kick magnitude versus time, that's actually coming from these horizons I was talking about. So not only is it an asymmetric emission of radiation, here you see that the asymmetry of the horizon itself, you could think about the curvature of this horizon as contributing to what slows down the kick in some scenarios. So I thought that's a really beautiful cartoon. So what is this going to teach us? Also yesterday, Alessandra talked about the harmonics. So I think it's totally sensible for the ground-based detectors to have focused on the 2-2 mode so far. This is the dominant quadrupolar mode. It's what you care about when you see face-on signals. But of course, we have the wealth of information available to us, and you heard from Alessandra all the work that's being done to get the models of gravitational waveforms to have all this at our fingertips, so we get the most science out as possible. Here is one example of how higher harmonics can really play a role in our really understanding what's happening as we shed black hole hair. So as we shed hair to come down to the black hole. So higher harmonics get excited because of the initial parameters of the black holes. So it just makes sense as you're going to generate and radiate energy in different harmonics depending on what the spins and magnitude the black hole masses are. So here is an example, because what also matters is not only what the initial parameters are, but the orientation of the binary towards the detector. So you'll turn on different harmonics, or you'll see different harmonics encoded in the waveforms, depending on the orientation with respect to the detector. So here is an example. This is the plus polarization of the gravitational wave versus time, where TC here is the time for coalescence. So 0 means we've had the peak after merger. Blue is a face-on, only 2-2 mode of the gravitational wave emission, assuming a Q equals 3 non-spinning black hole binary. And here you cannot see the difference between two other scenarios, 1 and 2, red and an orangey yellow. And that's because there's only the 2-2 mode. The difference between these two lines is the black hole kick is moving towards the detector for the red case and away from the detector in the yellow case. If we use the higher modes, if we actually reconstruct face-on versus edge-on with all the information available to us, you'll see a difference. So if a black hole is moving towards the detector, it has this little strange difference between it and the one moving away. So we actually have in the modes, in the gravitational waveforms themselves, information about which direction that black hole is moving respect to us. And so what we've been trying to do, what Juan is working on, is to exploit this difference to actually measure the recoil. It's very dangerous for me to put these plots up because I don't completely understand them. So this is all Juan's work, so I'll apologize. I stole this slide from him. He's giving a talk on this right now in Spain. The idea here is that we produce this population of numerical relativity waveforms. For Q equals 2 and 3, we could also have used model waveforms if they have all the higher harmonics in them, but we just get the harmonics when we do numerical relativity, so we use those waveforms. And we eject a signal from NR, and then we go look for that signal using numerical relativity again. So this is not a pipeline or anything like that. This is just a simple, cute task to see, is this possible? Is it actually possible to start measuring information about recoil from our detectors? So this is zero noise. It's just using one LIGO detector. It's a very preliminary type of experiment. And what it's doing is it's injecting a Q equals 2 mass ratio, and the total mass is 100 solar masses, so it's optimistically large. It means that we don't have to worry about too many in-spiral cycles. And then it goes and tries to recover, using a bunch of NR waveforms, what is the orientation of that kick. So trying to measure that information about whether or not the kick is pointing towards us or away from us. And this is that result. So the kick was actually 140 kilometers per second in magnitude. And then you can see, depending on which orientation it was, directed towards us or away from us, how well you can recover that orientation. So the white line is the actual injected orientation, which is hard to see, and these blacks are these colors are the posterior distribution of the measuring it. And it's not bad in this preliminary experiments. You actually could get at that information, which I think is very exciting. It opens up some more information we might pull from these binary black hole mergers. So what's behind all of this is our ability to predict what Einstein's telling us about strong field gravity in these binary black hole signals. And so I like to think of it as a map. We have a map from the in-spiral parameters to the ring-down parameters. This is just a cute little cartoon of a bell ringing to remind us that what ring-down just means is that the frequency of the gravitational radiation is uniquely described to a mass and spin of a curved black hole, if that's what we have at the end of the day, is a curved black hole, by its frequency of the radiation and its decay time. So this is from perturbation theory, and these are two modes that were arbitrarily excited, and you can see the beautiful decay of this mode. And I just point out this is a log plot, so this is an exponentially damped mode, which makes it really hard to detect in an actual detector with noise. So, but that's the beauty of it. You have these really simple, and once you're in perturbation theory, a really simple explanation of what that radiation looks like and how it could be used to predict mass and spin. And we're going to hear more about this later this afternoon. There's a series of talks on this type of thing. And I just will remind you that one of the nice outcomes of numerical relativity, rather than just the gravitational waveforms, were some formulas produced mostly by Carlos Lusto's group and Luciano Rizzola's group, which used, they provided fit formulas, basically say, give me the input of your initial black hole masses and spins, and we'll tell you what the final mass and spin are, the gravitational recoil, and more recently, the peak luminosity. So these things are provided. Not only that, but they are what was used to do consistency tests in LIGO. So this plot, it lost its label, but it said Abbott et al. So maybe that's not that useful. And this is the LIGO Virgo plot from the testing GR paper for the GW 150914. It's a beautiful paper, and it explains very nicely how you can measure the final mass and spin of GW 150914 using these kick formulas. So literally taking the in-spiral and taking those parameters that you measure from the data, using the numerical relativity waveform to predict the final mass and spin, doing the same thing for what happens after the in-spiral, merger ring down, and then comparing that information to the full template that matched the signal. So this is how this information is used now to check for the consistency of our gravitational wave detections with the predictions of Einstein's equation provided by NR. What we're not doing is measuring quasi-normal modes independently from the data, right? That's hard. That's unfortunately hard because it's really exciting, but of course we're just in the beginning of gravitational wave detection, so we shouldn't get depressed. This is a relatively old paper from one of my students who's now doing nice work at Cardiff, and there's been many such papers that have come out in the past and recently looking at how would you actually detect more than one ring down mode, quasi-normal mode. They're hard because they're exponentially damped. The strongest one is the 2-2, but we need two if you want to test the O'Hare theorem, if you want to find out if this is really an Einstein curved black hole or not. And what these plots are the noise curves versus frequency, and this little gray guy is advanced LIGO design sensitivity. This would be one version of Einstein telescope, and all of these colorful lines are different Fourier transforms of a ring down of a quasi-normal mode individually. So for example, this red one here is the 2-2 mode that we know and love. And this little green one, unfortunately, would be the 2-2-1. So a higher harmonic than we'd usually see of 2-2. And over here, this orange one would be 3-3. So that'd be the next most excited mode for this particular case of a Q equals 2. Change the parameters, we'll change that landscape of which modes might be excited. But the takeaway is just that it can be hard with current detectors to see these individual modes. Okay. And there's been more recent work on doing this, detecting these modes by many of these groups down here. And this is not a complete set of papers. People have looked at different scenarios, echoes, all sorts of, not echoes, sorry, stacking, all sorts of scenarios to be able to get at these quasi-normal modes. So, oops, see me in this thing, that's why I don't usually use them, because I'm just not good at it. So now what we're going to do is show you the whole talk again so you don't, it's a test later. Make sure we're paying attention, sorry. So we're going to, one of the ways this was used again, and here's the, this is the same paper, so now you have the citation, is check the consistency of the data again with that final mass and black hole, and this is for GW 150914. And so what you're looking here is that search for these quasi-normal mode decay times and frequencies. And what this plot demonstrates, so here is the signal, right? So this is the blue here is the 90% confidence, and the dark one is our actual template that match the data. And what we want is this ringdown. Now this looks beautiful because this is the picture of the template, not of the noisy data and how hard it is to get to that ringdown. But one of the questions is, when does ringdown start? We don't know that, right? We have to do it by actually comparing it to the data. So when you look at plots like this, all these different times, 7 milliseconds, 5, 3, 1, this is from measured, I think, at the peak, how much you wait before you say we've entered this perturbed regime of our damp sinusoid ringdown. So what this study did is it developed the IMR waveform, that's this guy, and it tested against a bunch of GR predictions using that damp sinusoid that we know and love. And you can see, depending on when you decided to measure the ringdown or call it ringdown, versus the full signals, quasi-normal modes that you would expect from the template, whether or not you're consistent with a Kerr-Einstein black hole. And the answer is it is consistent. But there's still a lot of work to be done to really prove whether or not we have truly Kerr black holes in nature. And we heard yesterday an update to this by Alessandra's group, who is actually parameterizing EOBNR to allow for freedom of these damp sinusoids so that we might actually get more information about whether or not we're consistent with general relativity. So is there an alternative? Ringdown kind of is hard to get at because of this damp sinusoid, because we're dropping so quickly into the noise. Is there any other information we could use from the merger to pull this out as we wait for detectors to get more sensitive? And so in an older paper with Jim Healy and Pablo Laguna, we looked at a correlation between frequency at the peak of the amplitude. So let me just take a second to describe this. This is an equal mass non-spinning black hole, so as simple as possible. These are a bunch of rescaled plots of the amplitude versus time. And this is, each color represents a different harmonic of the signal. So 2-2 is the loudest. They only are all lined up because we scaled them too, okay? So these other modes are much softer, they're much quieter. This line is when that common apparent horizon that I showed you as a purple or blue peanut in the second slide forms. So this peak in our amplitude, the gravitation radiation, happens quite a bit after a common apparent horizon is formed. So you can imagine that there's information about that final black hole already present in that peak if you can go find it. So what we found was that if we measured the frequency at the peak amplitude, we could correlate that with these little fits to the quasi-normal mode frequency. And depending on which mode we used, we could correlate that to the different frequencies for each quasi-normal mode, labeled 2-2, 3-3, 4-4, et cetera. And this is that plot. So this is a log of the quasi-normal mode versus the frequency at the maximum peak amplitude. Here's the 2-2 in blue, 3-3 in red, and so on. And then this is what that decay time looks like, because you need both pieces of information to get the final mass and spin. So we had these beautiful correlations at the time, and then we sort of just let it sit there. Got distracted by detections, who knows. And so recently I asked my graduate student, Deborah Ferguson, to pull this back out and start looking at it more realistically in the world that we live in with actual data, and figure out whether it's possible to actually make measurements of these peak frequencies and therefore determine the final mass and spin directly from the peak. So this is very preliminary. So what was the thing? Don't scoop us. Yeah. She's only a second-year student, be kind. But she already presented this to the testing GR group in LIGO and also at an APS meeting, so it's already too late. So this is how to fit the final spin versus a measurement of that peak frequency, so now an F instead of omega. And this is a new fit because we did all that information in the beautiful world of Psi4, which is how we measure gravitational radiation from numerical relativity, but the detector uses strain, so we had to redo everything in strain, and we decided to go directly to the final spin. So it is possible, each one of these lines is a different simulation again, and then a different measurement of the final spin, and each point here is the peak frequency associated with that waveform. So this is preliminary, obviously, it's not published yet. This is showing us actually making the fit to that peak frequency and recovering a final spin. And what she's working on right now is to do this in actual data to see could you recover GW 150914, for example's final spin. So we'll see how that goes, hopefully in the next couple weeks. So I'm also going to recover some Fred time. We're also nice to Fred. These are some challenges ahead, which is that we really just barely started exploring strong gravity in the universe. So I'm beginning to see, after a few years of us complaining that we should look for higher harmonics, they're getting their due now, because that's where we're going to break some degeneracies in our parameters. And also, I'd like you to walk away with the idea that we could get some new information based on being able to measure these higher harmonics in the gravitational waves. There's an incredible and I think exciting amount of work happening at this transition to Ringdown in the data. And so we're seeing a lot of, and we're going to hear more later about what ways we can exploit that to test general relativity and learn about nonlinear gravity. And of course, all this just gets better as the detectors get better. So exciting times ahead. Thank you. No question. Ilya. Yes. Oh, I'm not in control. I forgot. Okay. There's two. You guys have to decide.
Well, I actually had two questions, but I'll only ask one because I know Ramesh will object otherwise. So you were pointing out the ability to measure the kick directly from the waveform, and we're arguing that maybe at SNR of 25 you could do that. So the way I was thinking about this was that, okay, let's say you measure effectively a redshifted mass as usual from the late merger and Ringdown. The amount of redshifting you get relative to if you didn't have a kick, for example, is, okay, for a kick of, let's say, 300 kilometers per second would be 10 to the minus 3, right? So that means you have to measure the mass to an accuracy of 1 part in 10 to the third in order to be able to constrain such a kick. Which, if you rescale from how well we can measure the masses now that, you know, for SNR 20 or 25 events like GW 150914 suggests you need an SNR of 1,000. And from what I remember, this is when Chris Moore actually tried to do this calculation, he got sort of similar ballpark numbers. SNRs of 1,000 would be necessary, so he argued it would be doable with LISA, but not LIGO. So what am I missing? How can you do it with SNRs of 25?
Well, this is not right. This is not recovering. This is purely line of sight. So this is really figuring out the direction the kick is going, not its magnitude, right? So it's looking at what's being recovered, right, is that the fact that there's higher harmonics means that I can actually disentangle whether the black hole is moving towards you or away from you. So it's looking at that. So in that plot, I didn't change the magnitude. That was all injected at 140 kilometers per second. So all it was measuring was whether or not you were coming toward and back from the fact that you get these things. I don't see that you need this opti-millionth precision in mass to do that.
So okay, so I still don't understand, because the only real difference, right, is, yes, there's beaming, let's say, but that's an amplitude change and that's going to be infinitesimal, right? So it feels like the only real difference is
beaming, but you're looking at a difference in the modes. I feel like you're not looking at difference in modes when you talk about that. Yeah, the shape is different. But yeah. So, you want me to put it back up?
No, just to clarify that, I think Ilya is thinking that you're measuring actual Doppler shift.
Yeah, no, we're not.
But that's not what you're measuring.
No.
It's something from the waveform shape, yeah.
Yeah, it's actually the waveform shape, which is why you can disentangle, because the templates pick up the difference in the shape. So it's very different than just purely looking for that red shift, blue shift.
Yeah, Avi?
So my question is also related to this kick, but in fact I wanted to highlight that it's not LIGO that would be of interest here, it's LISA, because, well, first LISA will have a much higher signal to noise, but more importantly, it's the fact that when you kick a supermassive black hole, as a result of a merger, there could be an electromagnetic counterpart in two ways. One is that the broadline region will potentially have a shift, okay?
Yes.
A systematic shift of hundreds of kilometers per second, maybe 1,000, depending on spins. And the second would be the star cluster attached to that black hole that would move with it.
Yeah.
And so I would imagine that in the future with LISA, we could potentially measure the recoil electromagnetically.
yeah.
Electromagnetically. And that would be very interesting to
I
compare to
completely
your
agree.
calculations.
I completely agree. So Juan's focus has been LIGO, which makes sense. I mean, we're in the midst of it, but LISA opens it up to a much greater possibility. Yeah, I completely agree. We can argue later, Ilya. Anna?
So I had a question on this work that you did with Deborah Ferguson, right? So you could get this nice correlation between the spin and the peak frequency. But to do that, I presume you need to know the mass,
Yes, thank you. I
right?
meant to
How
mention
well
that.
do you need to
Yeah.
know it?
So I'm glad you mentioned that because it slipped my mind because I didn't write on the slide. Part of the problem with this correlation is because you only have one number, the peak frequency, you're not measuring mass and spin independently. So that's why we only recovered the final spin, and we assumed the knowledge of mass that we currently measure. So it's going to, I didn't show you, I only showed you a plot looking at how she measured, how she fit the final spin. But the two errors they're going to accumulate is the measurement of the final mass that you get from some other means, and also how well you can measure the peak frequency in the data. So we're more worried about measuring the peak frequency in the data than the actual error in measurement of the final mass you need, but they're both, and we just haven't finished that's why it's always scary to use a preliminary plot. But I think it's interesting, but we haven't done the final spin measurement yet. You need both. More questions?
So if there are no other questions, let's thank Deirdre and all the speakers.